All right, continuity. Continuity is a very important concept in calculus. It is a criterion, that's the singular of criteria, for several fundamental definitions and theorems, including the derivative. So we don't often use continuity as an end of itself, like do we care if it's continuous just for that? Not really, but it has to be continuous in order to do a bunch of other stuff in calculus, including having a derivative. So all the first semester is finding a derivative, finding the slope at a point, but if it's not continuous, there's no slope there, and you can't do a derivative. So continuity is super important because it's the foundation that we sort of build off of for other things. Okay, visually what continuity means. Let's just back up. Continuity just means you can draw the graph without lifting your pencil. So we could draw something nice and smooth. Maybe it's even got some jagged edges on there. But that would be continuous. For all values of x. And that for all value of x kind of suggests what's coming, and that is things might be continuous in one spot but not continuous somewhere else. So continuity at a point or at over a range is what we'll usually be talking about. That one's continuous everywhere. So can you think of types of graphs that you've seen that you couldn't draw without lifting your pencil? Like what kind of graphs would not be continuous? Or what kind of things would make a graph not continuous? Like an asymptote. I'm going to put that on the second graph to match my notes, but that's definitely one of them. So if there's an asymptote there, that would not be continuous. Let's just call that point A. Because it is continuous everywhere else, but at A, it is not continuous. I'm going to label it just so I can call it something. Let's call it h of x, because we're going to go in order here. F of x, g of x, and j of x. So we'll say h of x has, now you use the word vertical asymptote. We're going to use a different term that means the same thing. So there's some terminology today, like you already know the concept, we're just going to put a different name on it. You said vertical asymptote, that's exactly right. But when we're talking about discontinuities, we'll call that an infinite discontinuity. I guess in parentheses we can affirm what you already know, that yes, that's a vertical asymptote. So it has an infinite discontinuity at x equals a. So those mean the same thing. You can use those interchangeably. You know what a vertical asymptote is. Now just attach a new calculus phrase on it as well. Infinite discontinuity. Okay, so that's one type of discontinuity. What other types of discontinuity have you seen? Would a horizontal asymptote necessarily have a discontinuity?
No.
Yeah, it wouldn't. Or a hole. That's going to be the first example here. So let's just put a graph with a hole in it. Not continuous, so we'll say g of x has a, yes, it's a hole. Do you want to guess what calculus phrase we attach to that? What type of discontinuity it is, if this one's an infinite discontinuity? I mean, you're just guessing at this point, but what's that? Singular. That's not a bad guess, but singular has other meanings in math, so that word's already taken.
Is it restricted?
No, it's even easier than that. You guys are getting fancy on me. It has a point discontinuity. Which is a hole. So another one that's like, you know what a hole is, but now to sound fancy, we're going to call it a point discontinuity. All right, there's one more type of discontinuity, and you've seen this type as well. A jump. So who knows? There's some kind of jump there. I could be tricky and ask you what you think that type of discontinuity is called. Anyone want to take a guess? We finally hit one that's called what it ought to be called. Jump discontinuity. Let's put that one at A as well, at x equals A. Because we need to say at x equals A, because at other places, that graph is continuous. It's only at A where there's a problem. So that means later on, weeks and months from now, there's things that we can't do at A because it's not continuous. But if it asks us to do some calculus thing away from A, we might still be able to do it because it's continuous as long as we're not looking at A. Okay, now there's also categories of discontinuity. There's only 3 types, but we put them in 2 categories. So the first one is a category unto itself, and the other 2 share some characteristics. Like the first one, it feels like it's like not as extreme of a discontinuity. It feels like I could fix that, right? Like that would be easy to fix. Why don't we just fill in the point? What are we doing here? That's a fixable, not the official word, that's a fixable discontinuity. These other 2, you can't fix that, right, without significantly changing the graph. Like you'd have to change a lot of things to fix those. This one, if you could just fill the dot in, you'd remove the discontinuity. And so this one's called a removable discontinuity. You could fix it. I just fill the dot in and it's not discontinuous anymore. The other 2, they are not fixable, they are non-removable. You're stuck with those. Non-removable discontinuities. You sound really fancy today. I know when you go home, your parents probably ask you, what did you learn in calculus today? Well, Mom, we learned about non-removable discontinuities. You sound really fancy. That just means it's not continuous and I can't fix it. Okay, back up big picture, like literally zooming out here. So conceptually, it's easy to see what's continuous and what's not. Like I thought about standing at the door and showing graphs on the way in and just asking you if it was continuous or not, because you'd probably get it right. That's continuous, those aren't continuous. That's good, but now we put some technical language on there about point discontinuity, infinite discontinuity, jump discontinuity, and whether we can fix it or not. Okay, talk with a partner. I don't mind you talking with a partner, but writing your own definition for what a function means to be continuous is, that's like fishing and hoping you come up with it. That would be tricky for students to come up with. So I'm just going to give you the definition. F of x is continuous at x equals a. Again, because we're usually concerned about a certain point, if it's continuous or not. If and only if right? That's like that geometry thing. That means this is a bidirectional statement. You can use the if-then in either direction. That's what we use for definitions. So f is continuous if the limit, so here's our limits, as x approaches a from the left of f of x you might be able to fill it in from there. What do you think the left limit has to equal? By the way, this is a three-part statement. The left limit has to equal the right limit, right? Because if they don't go to the same thing, you've got to jump. So they've got to go to the same thing. So the limit as x approaches a from the right so they've got to approach the same thing, but there's one more thing that has to be true, especially if you look at this point discontinuity. This graph satisfies what we've said so far, right? The left limit equals the right limit for this picture. But it's not continuous, because not only does the left limit have to equal the right limit, those both have to equal the function at a. You will see this referred to as the three-part definition of continuity. Even on the AP test, very rarely do they ask you to use a definition or do something like super technical. It's mostly just using the stuff you know. But this one they can ask, and this one, I'm pretty sure I phrase it this way on the test. Use the three-part definition of continuity to discuss the continuity of this function at x equals 3 or whatever. And I'll be looking for this statement. And I mean, you can't just, you would start with that, and then you would fill it in and see if it works. See if the limits equal each other, and then see if that equals the function value. The rest of this we've kind of talked about. Let's go ahead and do it. Removable discontinuity. So that's the removable discontinuity. Which type of discontinuity is that? The one that we can fix? That's the whole. And now I'm thinking back to this definition. For a whole, the limits equal each other. The limit as x approaches a from the left does equal the limit as x approaches a from the right. But then it breaks down, because that does not equal the function value at a. That's like the technical definition of a removable discontinuity. So we got like levels of understanding what a whole is. You know what a whole looks like. We can fancily call it a removable discontinuity, and then we can even put this fancy definition on what it, or description of what it is. For non-removable discontinuities, non-removable, that's the jump and the asymptote. Where does our definition break down for a non-removable? Yeah, the left and right don't even equal each other. Limit as x approaches a from the left doesn't equal the limit as x approaches a from the right. Probably the most important thing on this page to remember is the three-part definition of continuity. And that's a lot of technical stuff in there. Maybe I should have put the kind of the slang way to say it. The left limit equals the right limit equals the function value. If the left limit equals the right limit equals the function value, we're continuous. If it breaks down anywhere, then it's not continuous, and where it breaks down sort of affects what exactly is going on, but all three things have to equal each other for it to be continuous. Again, easy pictures, kind of tricky on the technical stuff. Okay, let's use that and try some things here. Number 1, state the value of x, if any, at which the function has a discontinuity. Okay, again, I'm thinking left limit equals right limit equals function value. That's what continuity is. So that'll sort of guide my thinking the rest of the way here. Looking at A. Actually, I think you know A from pre-cal. Now we're just going to use it in a calculus sense. Do you know where A is not continuous? And why is it not continuous at -2? There's a hole there. Like you knew that from pre-cal. There's a hole at x equals -2. In fact, anything that makes the denominator 0, this one happens to be a hole, but even if something didn't cancel out, it would still be a discontinuity. It would just be a asymptote rather than a hole. Let's see, did we answer the question? State the value. Okay, it didn't ask for a specific type, but it could have, so I'm going to, like, in parentheses, say that's a removable discontinuity. That's giving more than an ask, but we should know that. What about part B? Where might it have a discontinuity? We don't know yet, but like right of one, we're on a parabola. Left of one, we're on a line. The only thing that might be a problem is at x equals 1. I'm worried about the left limit and the right limit. Do they meet up? So from the left, that would be, let's see, that would be branch B, because less than 1. So the left limit's -2. From the right, that means we're a little more than 1, so we'll be on branch A. 1 squared plus 3 is 4. Okay, so thinking back to our official definition here, the left limit does not equal the right limit, so it is discontinuous at x equals 1. And if it asks me to get specific, what kind of discontinuity is that? What's that? Oh, that's fine. It is non-removable. And more specifically, a jump. So we could ask lots of questions about that. We could just say, what does it have one? Where does it have a discontinuity? What kind is it? So lots of questions, lots of vocabulary that all centers around, yeah, this thing's got to jump at 1. Number 3, that's basically the same question, so we can throw out number 3. Number 2, let's look at number 3. Find the value of the constant k that makes it continuous. Okay, so that means I've got another potential jump. So my thought process, is there a jump at x equals 1? Like, I don't know yet. In fact, it's telling me that there shouldn't be. Like, make there not be a jump. So that means I want the left limit to equal the right limit. So instead of having a jump, I'm going to force them to go to the same spot. So the left limit, that would be part B at 1. So k times 1 minus 7. I want that to equal the right limit, so that would be part A, m squared plus 3. Let's see, k minus 7 equals 4, so k equals 11. If k is 11, then they match up. We like those kinds of questions. You will definitely see a question like that on the test. Like a find k question where you set part A equal to part B to make them equal to each other. 4, which of the following is continuous at x equals 1? The test is fresh in my head because I just put it in for copies. There's one like this on the test as well. Which of the following is continuous at x equals 1? Okay, so I just need to get a yes or no on all 3 of these. So really this is 3 problems in one. At x equals 1, this thing has something going on. You know what, let's factor the top. The x minus 1's cancel. And so so there's a hole at x equals 1. That's a removable discontinuity. And basically we're going to see if this other statement fills the hole. So there's a hole at 1. Does this thing fill the hole? I'll need the y value then at 1. So do you remember from pre-cal, if there's a hole at 1, how do you figure out the y value of that hole? Remember how to get the y value of the hole? You'll take that x value and just plug it back into what's left. So y equals 1 minus 1, which is 0. So there's a hole at 1, 0. So that's a removable discontinuity. Let's see, did they fill the hole with this second statement? So there's a hole at 1, 0, and there's a point at 1, 1. So discontinuous or not discontinuous? Not discontinuous. Is it continuous or not? No. All right, I don't know what the graph looks like, but the point's at 1, 1 and the hole's at 1, 0. It looks something like that. So that is not continuous. It has a removable discontinuity, but they did a terrible job. They did not remove the discontinuity. Like they should have put, if they'd have put this equal to 0, well then they would have filled the hole. They didn't do that though. Mm-hmm. So if x is 1, y is 1. Right, when x is 1, the function is 1. So that one's not continuous at 1. Where is this one going to not be continuous at? This is a tricky one. Not continuous at what value of x would be a problem? -1. So read the question though. Which of the following is continuous at x equals 1? So is this thing continuous at x equals 1? It is. So this one throws people off. It's like, oh, that's not continuous. Like, well, yes, you're correct, but it is continuous at x equals 1. And that was the question. So the location of the discontinuity matters. That's a tricky one. The last one is probably the easiest because this is just, does the left limit equal the right limit? So from the left, if you plug in 1, that's a lot of 1s to be careful about. Half of 2 is 1, 1 plus 1 is 2. And on the right side, we're just at 2. Those are equal to each other. Same left and right limits. So that one's continuous at x equals 1. Okay, so now let's make sure we answer the right question here. Which of the following is continuous at x equals 1? 2 and 3 are continuous at x equals 1. Tricky stuff in that one. Another K question. Yeah, we're good on time. Why don't you try 5 and 6, but I'm going to warn you that the answer to number 5 is not there. So it's not one of those answers. I'm just leaving it open-ended because I made a mistake on writing the notes. So try 5 and 6. So 5, you'll just set the two things equal to each other and figure out what K is, but it's not one of those answer choices. And 6 is just the vocabulary stuff, so that I don't have to deal with fractions. Anybody opt for this method? I could multiply through by something and make all my fractions go away. Yeah, let's multiply through by 8. Then I don't have to worry about common denominators and bleh. Let's multiply through by 8. So that would be K minus 4K minus 2 equals 48. Right. Way better than dealing with fractions. Negative 3K equals 50. So K equals negative 50 thirds. Again, you've seen two examples where it's a find K problem. I promise you will have one of those on the test. Find K to make it continuous.
Do we have calculators on the test?
You will not. I don't think it's that ugly, though. I think this one's just messing with you a little bit. Number 6, the graph of G, a piecewise function, all over the place here. Which of the following statements is true? Let's pick on people because I've talked too much. I'd like to hear from you. So just one person per statement. We just want to know if statements 1, 2, and 3 are true. And again, this helps me do names. So Alec, Maddie, and Ryan. Okay. Alec, statement number 1, as he checks with a friend, certainly okay. G has an infinite discontinuity at x equals 1. Is that true or false?
True.
That is true. Because what does infinite discontinuity mean?
Oh, you're asking me.
What's that?
You're asking me?
Yes.
Asymptote,
Vertical asymptote. So again, this is just a little bit of vocab. You already know about vertical asymptotes. Now we're going to also call them infinite discontinuities because we want to be fancy like that. Maddie, G has a non-removable, so non-fixable discontinuity at x equals negative 1. That's true. Why is that one true? Because it is a jump there. I can't fix a jump. So yeah, that one's true. And then Ryan, G has a non-removable discontinuity at x equals 2.
That's false because it's a hole.
Yeah, that's a hole. We could fix that if they would just move the dot into the hole, then we'd be good. So that is a removable discontinuity. A hole is removable. Okay, so which of the following statements is true? 1 and 2 are true. So answer C. which of the following has a jump discontinuity? Yeah, I want to do this one because this messes people up on the test. So this is like all kinds of hints today. Like all of this stuff's on the test. Which of the following has a jump discontinuity at x equals 3? Okay, so potentially they all do, right? Because like something's going on at 3. So let's check the left and the right for this one at 3. So left of 3, 3 squared minus 4 times 3 plus 1. Does that equal 1 minus 3? I'm checking the left and the right. Let's see, 9 minus 12 plus 1 would be negative 2. 1 minus 3 is negative 2. Right, the left equals the right. They're touching each other. They go to the same spot. So that one, wait, I put a check next to it, so I need to be careful here. It is not a jump discontinuity. It's not a discontinuity at all. All right, G, kind of the same setup. I need to check the left and the right and see if they equal each other. So the left-hand side would be 3 squared plus 3 times 3. The right-hand side would be 4 times 3. 9 plus 6 does not equal 12. So that does have a jump discontinuity. And then H, it's not really like left and right, it's just like at 3 versus not at 3. So at 3, that would be this one. 3 squared minus 6, 9 minus 6 is 3. Not at 3 would be the other one. 2 times 9 minus 5 times 3 plus 2. 18 minus 15 plus 2. 3 plus 2 is 5. 3 is not 5. So that's not continuous. Is that a jump discontinuity? What kind of discontinuity is that? They're not continuous because they're not equal to each other. When x is not 3, we're on this parabola. When x is 3, we're not at that spot. I don't know what this looks like, but that's a hole. So that's not a jump discontinuity, that's a hole. So that is kind of tricky because that's not, it is a discontinuity, but it's not a jump discontinuity. So the only answer that's correct is G. That's the only one that has a jump discontinuity. That's tricky.
So when they set equal to each other and then they're like, they have equal sign and then they're not equal to each other, that's a
Well, but this one was not equal to each other and it was a jump. It has to do with this stuff up here. Left of 3 versus right is 3. That's setting up a potential jump. If I'd really been paying attention, this was never going to be a jump discontinuity because of how this was set up. So if I'd really been watching, that was not ever going to be a jump. So I didn't really even need to work that part of the problem. All right. By the clock and by the notes, we're almost done. So the next assignment is whatever the next worksheet is, worksheet 4. Good news is tomorrow I feel like is a little easier. IVT and squeeze theorem are easier than continuity, and then we got 2 days of review. So try the continuity stuff tonight, but we'll review it tomorrow, and then we're kind of on the downhill for what's on the first test.
It's at the bell. So.
Okay, but I probably need to sign it. There you go. Remember, this might come back to bite me saying this.